thank you very much, Adriana. Thank you very much to the organizers for giving me this opportunity to give this talk. I'm going to talk about a work I've done with Antonio Ferreiro. You can see all the technical details are in this paper that we published recently in PLB. And as I'm going to talk about regularization in cosmological spacetimes. In particular, I'm going to talk about probably the easiest thing you can do, which is to regularize the two-point function of a free scalar field, okay, in a cosmological spacetime. I'm going to talk about how we can regularize it so that we don't distort so we get rid of the ultraviolet divergences, but we don't distort what's happening at the infrared scales, okay? Okay, yeah, great. So of course, we are in a quantum field theory workshop, so I want to work in the framework of quantum field theory, right? And we are working in curved spacetimes. I'm going to talk in particular about the expanding universe, which is parameterized by this Platt-Feldman-Robertson-Walker metric, right? And we know that if we put these two things together, what the result that we get is that there is an amplification, okay, of field fluctuations due to the expansion of the universe, okay? We have an amplification of matter fields, of the fluctuations of matter fields or of metric fields, okay? So in particular, I cannot, no, but I can use this. So in particular, no, the inflation, we know that there's an accelerated expansion of the universe sustained by the slow decay of the scalar field. We can compute this amplification of the fluctuations, and we get that due to this inflation, it gets produced a quasi-scale invariant over a spectrum of both the scalar and tensor perturbations. Okay. So this is the framework in which I'm going to work. Let me now introduce the equations. As I was saying, I'm going to consider a Feldman-Robertson-Walker spacetime, and I'm going to consider the equation of motion of a scalar field, of a free scalar field. I have also added a non-minimum coupling to the scalar curvature, okay, just for completeness. Although I will set this to 0 in the example I'm going to consider. And you can consider the equation of motion of the scalar field modes, okay, which is written like this, right? And the modes follow this normalization condition. Yeah, now it works. I don't know why. And then from this, and basically taking this the scalar field, decomposing it in integration and destruction operators, and taking the vacuum state, sandwiching the vacuum state. Okay. Then you can compute the two-point function. Okay, the two-point function, right? At different spatial points. Okay, I'm just putting the same time in both fields, but I'm putting different spatial coordinates. Okay, so it takes this shape. Okay, and in particular, I'm going to consider what happens when we put the spatial coordinates. So we evaluate this where the two fields are evaluated at the same space-time coordinate. Okay, so then we can write this as the interval over momenta of this function, which is the power spectrum that depends on the field modes. Okay, the field modes squared divided by a squared. Okay, I'm going to consider this power spectrum, and sometimes it works and sometimes it doesn't. I don't know why. Okay, so then we consider a specific case of the Sitter space, right? In the Sitter space, I'm going to consider, I'm going to introduce this parameter mh, which is the ratio of m of the mass of the field divided by h, okay? The Hubble parameter, which is constant. This is the scale factor in the Sitter space, right? And then we know there is a preferred vacuum in this space, which is the advanced status vacuum, right? Which depends on the Hubble, on this Hankel function of the first kind, when this parameter nu, it's the right? The square root of this number. So what is the power spectrum in this case? What we get is the following. Okay, we get this function here, where I have defined this variable x as the ratio between the physical momentum, okay, k over a, divided by the Hubble parameter, okay, which is constant, right? So this is the plot of the power spectrum, right? The black line is exactly this function, right? You can see that this for a very small mass, so m is just 10 to the minus 2 times the h. Okay, and you can see that in this case, right, you have at super horizontal scales, we have this scale invariance, right, and then at sub-horizontal scales, then this power spectrum grows with k, right? And here the gray line is, I have also depicted Minkowskian subtraction term. Okay, so just 1 over the square root of the frequency of the mode, and you can see that if we take the black line, right, this, and we subtract the Minkowskian vacuum, we get a scale-invariant result at all amplitudes. Okay, this is quite standard, but now we know that we are computing. I don't want to go back to the slides because then I don't know if we'll be able to return. But basically, the 2-point function is the integral of this power spectrum for all cases, right? Okay, so then the 2-point function is going to be infinite, right? And we need to regularize this. Okay? There are several. This is exactly what I have said, right? The 2-point function at the coincident limit has ultraviolet, quadratic, and logarithmic divergences, right? And then we need to apply a regularization method in curved space-time to subtract the divergences and obtain a physical finite quantity. Okay, this has the previous speaker has explained this in a lot of detail. Basically, we need to subtract to the 2-point function, right, the singular part, so we get a finite result. In Friedmann Robertson Walker space-time, we have the advantage that we can decompose this as an integral over momenta. So basically, what we are going to do is to take the power spectrum and subtract inside the interval, right, some subtraction terms, right, which we are going to define now, and then the result is the regularized power spectrum. Okay. Of course, this is not a unique procedure. We know that there are ambiguities in curved space-time when we do this regularization procedure, and in fact, there are two regularized 2-point functions can diverge, right, as a sum of 2 covariant quantities, m squared and r, where alpha and beta here are numbers. Okay. So different regularization procedures, or two different regularization procedures, when we compare the result, is going to give different values for alpha and beta. Okay? So the previous speaker has introduced adiabatic regularization, so that's really nice. So I don't have to explain it in detail, but basically, adiabatic regularization, we take the adiabatic expansion of the field modes. So we take the field modes, right, and we do an adiabatic expansion such that higher orders. So we take here the frequency, right? Well, not the frequency, but a functional W, right, in which omega 0 is the frequency of the mode, right? And then we expand this to higher and higher orders, right? Where higher orders of the expansion incorporate higher derivatives of the scale factor. Okay, so the second adiabatic order, for example, involves second time derivatives of the scale factor. So basically, due to the dimensional reasons, higher orders in adiabatic expansion give you higher orders of momenta. So by expanding the quantity, the integrand of the quantity we want to regularize, and subtracting the first adiabatic orders, we can get a finite quantity. Okay, this is adiabatic regularization. And basically, for the 2-point function, we can check that it's enough to subtract up to second adiabatic order. Okay, so with adiabatic regularization, we get these subtraction terms here. Now it doesn't work. This I don't know why. So, okay, we get these subtraction terms. Okay. Okay, so what happens? Well, from this we can compute the regularized power spectrum, right? It's defined. I don't know if I have defined it. I think I haven't defined it anyway. Yeah, we can get the regularized power spectrum, right? Which is this one. Okay, this was computed by Leonard Parker in 2007, right? And then let's plot this function. Then what happens is that due to these subtraction terms, right, there is a wrong sign here. This is larger or equal. Okay, so basically what happens is that if you have what we have is that for values of k that are larger than the mass of the field, larger than m, then this suppresses the amplitude of the power spectrum very strongly. Okay, you can see it here. This is the regularized power spectrum. So basically, the problem is that if we have a very small mass, which is typically the case we are interested, because it's the case that excites the fluctuations, right? What happens is that the power spectrum changes drastically, right? And in fact, for the massless case, exact massless case, the regularized power spectrum is 0. Okay, and this in fact was explored. I don't know. this was explored by in 2009 by Iván Agulló, Navarro Sala, Solomon and Parker in these letters, and basically they realized that if we do this regularization procedure, this can change the standard results of the slow roll inflation. Okay, so basically this is the motivation of So basically, the motivation of our work, the work that I've done with Antonio, is to see if there is a regularization procedure that somehow regularizes the ultraviolet divergences, but doesn't change what's happening in the infrared scales. Okay, so we preserve this scale invariance of the power spectrum. For this, we used an extended adiabatic regularization procedure that was developed by Antonio and Pepe Navarro Salas in 2019, in which basically the zero order of the expansion here is not taken as the frequency of the mode, but is taken as square root of k plus mu squared a squared, where mu is an arbitrary mass scale. Okay, it's a parameter that an arbitrary parameter that you introduce in the system, and this is related with the ambiguities of the renormalization procedure I was commenting before, right? This allows us to consider more generic renormalization regularization procedures, right? And if you put mu equal m, you recover the traditional adiabatic approach. So basically, yeah, you take the field modes that you can, the field mode equation that you can write in this way, okay? And the rest is the second order, okay? The second order term, and you just introduce the template here, and you solve order by order, right? And you get these new subtraction terms, okay? Then which now depend on this omega k tilde, which is square root of k squared plus mu squared a squared. Okay, this is nice, and this is a step in the good direction, because then, I mean, you can see it here from the equation that if you put a mu, which is large, then the effective mass term here is going to be very large. So you're gonna tame the distortions at infrared scales. Okay, the larger the mu, the better. The better you keep the infrared distorted. But this has a problem. The problem is that this does not give a zero in Minkowski spacetime. Okay. So basically, what we did is to take these terms. Okay, these are the same. So I was mentioning before, and then in the Minkowski part of the terms, these are I don't know. It doesn't work. That this is the third of zero over part of the adiabatic subtraction terms. Then we set there only here mu equal m. Okay. So basically, Minkowski, all of this is zero because a prima is zero, and we get the Minkowski maximum. And then we could just do this, but then we want to keep the infrared as undistorted as possible. So then we realize that this piece is finite when you integrate it, because it goes as k to the 5, right? So when you integrate it, k to the minus 5. So when you integrate it, this is finite, right? So then we just remove it. If we want to keep the subtraction terms as minimal as possible, right? The less, the better. So basically, yeah, this is the final subtraction terms we arrived, in which I have substituted this mu by this m, capital M, but it's the same, okay? And then this m, capital M, is an arbitrary scale. This allows us to define a regularized power spectrum, and then we just need to check that the subtraction, the difference with the regularized two-point functions, using our new method and using the adiabatic method, it can be written as a sum of covariant terms, and this is the case. Okay, so we are good. Okay? This procedure is valid. Fine. So then, using these subtraction terms, we didn't compute the new regularized power spectrum in the sitter, which depends on this M8, which is the ratio of M over H. Okay? And here I show what happens for different values of capital M. Okay, so the orange one is the adiabatic one, and then the different blue lines are the different, are this power spectrum, right? The new power spectrum regularized with our new terms, right? For different values of capital M. Okay, and you can see that as you increase capital M, then you keep, this is 0.1, this is 1, this is 10. So you keep, as the larger M8, the larger you keep the infrared undistorted, right? And in fact, for M equal H, you can basically have here a scale invariance, right? And then you can keep a scale invariance for all super horizon modes, and then have an exponential decay for super horizon ones. Exactly. So M equal H removes the UV tail while preserving the infrared amplified part of the spectrum. This is the result, the same result for a field with a larger mass. This is 0.5 M equal for 0.5 H. It doesn't work right now. So you can see that it preserves also the tilt of the power spectrum at infrared scales. Yeah. Okay, so this is my final slide. We have done this for the 2-point function. We are currently working on in the regularized stress energy tensor. I think we have already good results. They will be published at some point this year, hopefully, right? Yes, so and then in this case you have more ambiguities, but then we can also play with these ambiguities, so we keep the infrared part of this energy density and the pressure undistorted. And so this allows us to use Einstein equations to interpret the subtraction terms as renormalization of complete constants. So that's also useful. And then of course, we have worked with a scalar field, free scalar field, but also our idea is to extend this to other field species like fermions or gauge fields, and also to other scenarios in which you have interactions, for example, to interaction of the scalar field to a homogeneous time-dependent field like in field. Which is also, I think, an interesting application. And with that, I have finished. So thank you very much for your attention.
We have time for several questions.
Hi, thank you for the talk.
Thank you.
I have a question. So I don't know which slide, but you showed us that you can choose mu to be equal to a certain value, equal to the mass, only in the first two terms of an expression that you call Q. So, yeah, there. Yeah. Why can you do it, and why you don't fix mu equal to m in the other terms?
So, I mean, the reason, so we want to have mu in as many places as possible because this increases the ambiguities that we can have, right? But the issue is that we need that the 2-point function must be 0 in Minkowski spacetime, okay? And then that piece does not give you. So this basically this subtraction terms must be 1 over omega k in Minkowski spacetime, and this is not 1 over omega k.
I understand, but in the third term, you also have mu. You're not fixing mu there.
No, because that term appears at second adiabatic order, so there is no need to fix there mu equal to m.
Okay.
Because we want ambiguity there precisely to play with this parameter and keep the infrared part undistorted.
Okay, thank you.
Yeah, so regarding this slide, so you said that you test that your prescription is okay because it can be written as a sum of geometric ambiguities, but maybe this is a bit tricky, and it works because the 2-point function is maybe easier. But did you check that if you, or maybe it's future work, as you said in the last slide, that if you do the same with the stress energy tensor, the ambiguities that you obtain are compatible with Wald axioms? Do you have?
Yeah, we have checked that.
Okay.
We have done this is not published.
Okay.
We are working it right now, but yeah, we have a way of extending the subtraction terms in the stress energy tensor so that you have ambiguities. In fact, you have more ambiguities. And these ones are compatible with the ones of the 2-point function and simultaneously allow us to keep the infrared pattern distorted.
Okay. So then, yeah,
so
because it's curious because I feel a bit tricky. Like you fix mu here, then here you do nothing, then you cancel the other. So yeah, it's very nice.